हॅलो. हॅलो माले सर.
सर ये आता लाईव्ह स्ट्रीमिंग आहे.
हॅलो.
हा सर,
हा बोला ना.
लाईव्ह स्ट्रीमिंग चालू आहे आता.
लाईव्ह स्ट्रीमिंग चालू झाली. ओके.
हो हो, तुम्हाला लिंक पाठवतो.
युट्यूब. हो युट्यूबची का?
हो.
हा ते सरांना मी केला होता मेसेज. हॅलो.
हा बोला.
हा सरांना मेसेज केला होता पण ते लाईट गेली वाटतं त्यांच्याकडे थोडस. हे
हा
काय हे घे. आता काय बोलू का तिथे ते कर वाजू का तिथे आवाज नाही. तर ते लाईट
लिंक सध्या शेअर नका करू ना.
हॅलो.
हॅलो.
हा मॅडम नका सर जेव्हा जॉईन होतील ना तेव्हा आपण लिंक शेअर करू.
हा तेच.
हो हो. हॅलो हा मॅडम फक्त आपल्याला ना युट्यूबची लिंक शेअर करायची आहे आपल्या ग्रुपवर.
म्हणजे झूमची आपण कोणाला द्यायची नाहीये का?
हा नाही नाही शक्यतो नका देऊ आपण.
हम्म.
हो हो.
हॅलो राजपूत सर, सरांना फोन करा ना पुन्हा.
हॅलो हॅलो, मी
sir,
ऑनलाईन आहे.
नाही सर, तुम्ही आहेत, पण जे स्पीकर आहेत आजचे रिसोर्स पर्सन,
ओके ओके
कनेक्टिव्हिटीचा प्रॉब्लेम आहे.
अच्छा अच्छा.
म्हणून त्यांना एकदा कन्फर्म करायला कॉल करायला की काय झालं.
नाही, अगदी प्रॉब्लेम असेल, होत नसेल तर मग पोस्टपोन करता येईल.
राजपूत सरांना तेच मी सांगते की त्यांनी फोन करावा एकदा सरांना.
ओके.
हो सर, हो, मी केलाय मॅडम, फोन केलाय. ते जॉईन होतीलच, थोड्यात जाऊन होतील. हॅलो 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 हॅलो.
येस राजपूत सर, आवाज
हा
येतो.
हा हा, आवाज येतोय
सर
ना?
जॉईन
जॉईन
झाले.
झालेत सर आता.
हो
मी तर लिंक शेअर करतो मी आता स्टुडंटना.
ओके.
हो हो.
हॅलो.
हा सर.
येस सर.
राजपूत सर, पहिले स्क्रीन शेअर करा जरा.
हॅलो हॅलो.
स्क्रीन शेअर करा सर, स्क्रीन.
हा, माले सर. माले सर. हॅलो माले सर.
सर मी ऐकतोय.
हा सर, सरांना को होस्ट करा आणि जी स्क्रीन बनवली ना ती पण हे करा, ओपन करा, वेलकम स्क्रीन. हॅलो. हा मॅडम.
हॅलो.
हा मॅडम बघितली स्क्रीन.
हा पण स्क्रीन मध्ये सर सरांचं नाव तुम्ही ऍड नाही केलेलं. तुम्हाला सांगितलेलं ना एका ठिकाणी हेड ऑफ डिपार्टमेंट आणि एका ठिकाणी प्रिन्सिपल. ठीक आहे आता राहू देत सर. वी विल कंटिन्यू नाव. वी विल स्टार्ट.
स्टार्ट करू मॅडम. युट्यूब वर पार्टिसिपंट आले का? हॅलो. 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 पाटील मॅडम.
तर आपण स्टार्ट करूयात. मुलं होतील ऍड.
22 पार्टिसिपंट झाले आता.
हा 28 दिसतायत मला पण.
हो आता 28 झाले असतील. मी आता एक मिनिटापूर्वी बघितले 22 झाले. करू जॉईन स्टार्ट करू मॅडम.
येस सर. येस सर.
हो. Welcome all of you, dear chief guest, dear students, respected principal sir of Arts, Commerce and Science College, Onde, Dr. Chidna Patil ma'am, HOD, Department of Chemistry, Arts, Commerce and Science College, Onde, and all the staff of Department of Chemistry, Arts, Commerce, Science College, Onde. The today's chief guest, Mr. Vishnu Adole sir, welcome. Today's lecture on spectroscopy and organic chemistry. Now, I would like to all participants and the staff for national anthem. Now, I would like to request Dr. Pednekar sir, Principal of Arts, Commerce, Science College, Onde, to speak a few words.
Good morning, everyone. First of all, I welcome Professor Vishnu Adole as a resource person on behalf of ACS College Onde. Friends, organic chemistry has become a very important branch in the today's modern world, and the special techniques related to that branch is going to explain us. See, each teacher has got its special skill, special set of knowledge. So I request students to please pay attention and ask doubt, if any, at the end of the session. Thank you and best of luck for the webinar. Thank you.
Thank you, sir, for guiding us and wishing. Now, I would like to request Dr. Chetna Patil ma'am introduce our chief guest, Professor Vishnu Adole, sir.
Good morning, everyone. It gives us an immense pleasure to announce that we are conducting an e-lecture on spectroscopy and organic chemistry. The resource person for today's lecture, Professor Vishnu Adole, sir. He is an assistant professor from Arts, Commerce and Science College, Manmad, District, Nashik. Sir is gold medalist of 2010 batch from Savitribai Phule, Pune University. He have published more than 10 research papers in the Springer, Wiley and other reputed national and international journals. He has published book on intermediates and rearrangements in organic synthesis. He has also published in Himalaya Publishing House. He have filed Indian patent in last year. He is reviewer of journals like Chemistry Select, Journal of Applied Pharmaceutical Science, Material Science, Research India, and other reputed journals. He have prepared several YouTube lectures for the student. Sir has delivered several lectures as resource person in on various topics and also on net and set workshop. Sir has worked as NAC coordinator at ACS College, Surgana. He has also worked as ASH coordinator in ACS College, Surgana. He is an IQAC member in ACS College, Surgana, RUSA committee member, cyber security and human right course in charge in LVH College, Nashik, skill development course in charge in LVS College, Nashik, and a best chemistry student competition in charge. He stood first in the set paper 3 examination, which was held on 8th August 2010. I'm very glad to have such a dynamic personality for today's lecture. Sir, I welcome you from our college, our department, and I welcome to all the participants for this lecture. Thank you.
Thank you, madam. Now, I would like to request the chief guest of today's session, Mr. Vishnu Adole, sir. Please start.
Sir, am I audible?
Yes, sir. Yes, sir.
Sir, am I audible?
Yes, sir. You are audible, sir. Hi, sir. You are audible, sir.
Am I audible?
Yes, sir. Audible, sir.
Okay. Can I share my screen?
Yes, sir. Yes, sir.
First of all, I would like to thank Dr. Chetna Patil Madam, HOD, Department of Chemistry, for giving nice introduction. And also, I'm very thankful to Dr. Rajput sir for inviting me as a resource person for guiding TYBSc students. Sir, is it my screen visible?
Yes, sir. Yes, sir. You proceed, sir.
Okay. So
Okay,
I
sir.
welcome all students for today's lecture. And today we are going to discuss on very important topic of organic chemistry, and that is none other than spectroscopy. Spectroscopy is considered as one of the valuable topic for organic chemists, and you will find number of competitive exams are asking various questions on spectroscopy, and it is one of the important topic for chemistry students. Friends, first of all, before learning spectroscopy, we must understand why we are dealing with spectroscopy. We must understand why we are studying spectroscopy. So, first of all, I would like to discuss few applications of spectroscopy that will give you clear-cut idea why spectroscopy is important for us. So friends, very important thing about spectroscopy, we can find out structural information about the unknown compounds. So if we don't know the structure of the compound, we can find out the structure of that compounds by using spectroscopy. So structural information can be obtained by using spectroscopy. There are various spectroscopic techniques, and these spectroscopic techniques gives us valuable information, and different spectroscopic techniques gives us different type of spectroscopic information, and due to this spectroscopic information we get idea about different kind of structural informations, and all these structural informations are very important to find out the structure of the unknown compounds or to confirm the structure of compounds which we don't know. Then I would like to point out here some spectroscopic techniques which are very important in organic chemistry. The first important spectroscopic technique is UV visible spectroscopy. And dear students, I would like to tell you, by using UV visible spectroscopy, we can find out conjugation in organic compounds, and also very importantly, we can find out stereochemistry of alkenes. Dear students, we know that alkenes have two type of configurations, cis and trans, and we can easily find out the stereochemistry of alkenes. That is, we can easily predict configuration of alkene, whether it is having cis or trans, by using UV visible spectroscopy. And in today's lecture, I will deliver a talk on UV visible spectroscopy. So you will learn how UV visible spectroscopy is important to find out conjugation and stereochemistry of alkenes. So this kind of information can be obtained by studying UV visible spectroscopy. Second important technique, which is very important as far as organic chemistry is concerned, is IR spectroscopy. IR spectroscopy is also known as vibrational spectroscopy. And friends, by using IR spectroscopic data, we can find out functional group. We know that organic compounds are having different kind of functional groups, and information about this functional group can be easily predicted by studying IR spectroscopy. So IR spectroscopy is very important for finding what type of functional groups are present in the compounds. Then third important spectroscopic technique is proton NMR spectroscopy. Dear students, we know that organic compounds are composed of carbon and hydrogen. So basically, the organic compounds having skeleton of carbon and hydrogen, and as organic compounds are made up of carbon and hydrogens, the information about hydrogen is very important for deciding, for finding the structure of the compound. So if we know the information about how many types of hydrogens are there in the organic compound, we can elucidate, we can find out the structure of the organic compound. The third important spectroscopic technique as far as organic chemistry is concerned is carbon NMR spectroscopy. And by using carbon NMR spectroscopy, we can find out the information about number of carbons. As we know that carbon is the backbone of organic compound. If we get the information about the carbon, then it will be very valuable for predicting the structure of unknown compounds. And the last one, the mass spectrometry. By using mass spectroscopy, one can predict the molecular weight of an unknown compound, and by using molecular weight and by applying certain rules, we can predict the molecular formula of unknown compound. So dear students, by applying suitable spectroscopic technique, we can find out the suitable structural information about the unknown compounds. So spectroscopy finds very crucial importance in the organic chemistry. So in this way, friends, the structural information can be predicted by applying spectroscopic technique. So now we know the importance of spectroscopic technique, why it is important as far as chemistry is concerned. Now let us understand what spectroscopy technique means. Friends, it is very important to understand what is spectroscopy means to us. So we are going to see here what is spectroscopy in this slide. So friends, I would like to tell you, spectroscopy is the branch of science that deals with the study of interaction of electromagnetic radiation, that is light, with matter. So by this spectroscopic technique, as we know that we can find out the structural information. Now we are dealing with what is exactly spectroscopy. So what happens in this spectroscopy? What is exactly the principle of spectroscopy? The electromagnetic radiation means light. When light is passed through the matter, we know matter has three important states: gas, solid, and liquid. So whenever the electromagnetic radiation, that is light, is passed through the sample, you can see here in this slide, whenever electromagnetic radiation is passed through the sample, I have written here a rectangular box to mention a matter. So matter is there in the rectangular box. Whenever electromagnetic radiations are passed through matter, what is going to happen? The electromagnetic radiations can interact with the matter. There will be interaction between electromagnetic radiation with the matter. Matter in spectroscopy. So spectroscopy is study of interaction of electromagnetic radiation with matter. This interaction is very important in this spectroscopy, and depend upon type of interaction, there are various spectroscopic techniques. So electromagnetic radiation is interacting with the matter when electromagnetic radiations are passed through the matter. Now, if we take the example of water placed in a beaker, and if we pass sunlight through that beaker, we know that the water from the beaker is going to absorb the sunlight and the temperature of the water will increase. So we can say that whenever light is going through that beaker, water is absorbing the energy, and there is interaction between water molecules and the sunlight. So this interaction, study of this interaction, is nothing but spectroscopy. So here in this slide, I have mentioned two important things. So whenever electromagnetic radiations are passed through the sample, that is matter, whatever may be the state of matter, gas, solid, or liquid, whenever electromagnetic radiation is passed through the matter, so two things are possible. And these two things are, the electromagnetic radiation will pass as it is, that is, light is transmitted. And second thing is, which is going to happen here, is absorption of light. So the matter can absorb the light, or the matter can transmit the light as it is. And whenever light is transmitted, this means that the matter is not absorbing the radiations. Matter is not absorbing the light. Now, whenever light is absorbed by the sample, whenever light is absorbed by the matter, the thing which is going to happen there is increase in energy. So as matter is absorbing energy, the energy of matter will increase. As I took the example of water, when sunlight is passing through water, the light is absorbed by the water, and we know temperature of the water increases. Temperature of the water increases. This means that energy of the matter increases. This is very important. So matter is gaining energy when light is passed through the matter. So this is important thing. Now, as I discussed with you, the matter is absorbing radiations, matter is absorbing light, and when light is absorbed, and here what we are doing, the amount of light absorbed is studied in the spectroscopy. Means what kind of light is absorbed, how much light is absorbed by the sample is studied, and when we study the amount and what kind of light is absorbed by the sample, then the spectroscopic technique is called as absorption spectroscopy. And here the last slide, as I discussed with you, UV visible spectroscopy, IR spectroscopy, proton NMR spectroscopy, carbon NMR spectroscopy, all these techniques are absorption spectroscopic techniques. Means in all these techniques we are studying amount of light absorbed by the sample. And on the other hand, mass spectrometry is not an absorption technique. Mass spectroscopy is not absorption technique. Dear students, again I am repeating, UV visible spectroscopy, IR spectroscopy, proton NMR spectroscopy, and carbon NMR spectroscopy, all these are absorption techniques. Means in this spectroscopic technique, we are dealing with study of amount of light absorbed by the sample. Whereas on the other hand, mass spectrometry is not a absorption spectroscopy technique. This means that here in mass spectrometry, we are not dealing with study of amount of light absorbed. And you can also see here the names of techniques. UV visible is a spectroscopic technique. Similarly, IR, proton NMR, carbon NMR, all these are spectroscopic techniques. And mass is not a spectroscopic technique. Mass is a spectrometric technique. So there is difference between these four techniques and mass spectrometric technique. The spectroscopy is nothing but study of light with the matter, and here the interacted light, that is absorbed light, is studied with the absorption spectroscopy. Now at this stage we know that why spectroscopy is important and what is spectroscopy. So by these two slides I have differentiated the applications of spectroscopy and the meaning of spectroscopy. With this I will move forward. Friends, now as I discuss with you the electromagnetic radiation, that is light, which is interacting with the matter. Now we must understand what is meant by electromagnetic radiation. Now to understand the electromagnetic radiation, I have considered a wave propagating from the origin. Now here you can see I have placed a wave, and wave has two properties. So you know, you have studied in the 12th science, in the physics, the wave has two properties, and here wave has electric and magnetic properties. I will discuss these electric and magnetic properties in detail. First of all, let us see what is electromagnetic radiation. Friends, dear students, electromagnetic radiation consists of discrete package of energy which are called as photon. So photons are present in the light. Photons are present in electromagnetic radiation, and they are present in discrete packets. Photons are also called as discrete packets. We are not going in detail about the photons because it is not important as far as organic chemistry is concerned. Now you only remember electromagnetic radiation means light, and light means photon of energy. Now let us discuss this wave in detail. Now you can see here in this wave, the wave is propagating from origin, and here the electric field is oscillating in upward direction and the magnetic field is oscillating perpendicular to the electric field. So here we can say that electric component and magnetic component in the wave are perpendicular to each other. So this is very important, and every student from science knows this thing, that electric component and magnetic component in the wave are perpendicular to each other. And we also know that light is traveling in the air in the form of wave. So light is present in the form of wave. So light is having wave character. Light is also having particle character. So we are not going in detail in that physical chemistry part. You only remember here the electromagnetic radiation means light. Light is having photons, and here the light is having two characters, electric character and magnetic character, and these two characters are perpendicular to each other. In this way, we know about the electromagnetic radiation. Now, we know what electromagnetic radiation means. Now, let us see what is electromagnetic spectrum. This is very important for us. So, dear students, you can see this slide. You can take the screenshot of this slide. So, I have placed different types of electromagnetic radiations here according to their energy. So, I have placed here gamma rays, X-rays, ultraviolet rays, infrareds, radar rays, FM, TV, shortwave, and AM. So here you can easily see the energy is arranged in the increasing order. So it is arranged in the fashion of increasing energy. So what is important here? So as far as today's lecture is concerned, I will specially deal with UV visible spectroscopy. So different types of radiations are written here, and here you can see the UV visible spectrum is given. Now you may be confusing or you might be getting doubt regarding what this spectrum means. I will discuss this spectrum in the next slide also. What is exactly this spectrum? So in this slide, you only remember different types of radiations are given, and different types of radiations are having different type of energy. And for today's lecture, as I am dealing with UV visible spectroscopy, you must understand what type of UV visible radiation are there and how much energy UV visible radiations are having. So here in this slide, you can easily see the UV visible part is written here, and ultraviolet rays are having energy corresponding to 10 raised to 2 to 1 power, and here the visible part of the spectrum is written below. And I would like to point out here a very important thing. Whenever any compound absorbs visible light, that compound shows color. So the color which is visible to you, the color which is visible to us is due to visible part of the spectrum in the nature. So whenever any compound absorbs the light, then what is important thing? Whenever it is absorbing light in the visible part of the spectrum, it appears as a color to us. So I would like to tell you here, we all know the tomatoes. So in tomato, lycopene pigment is present, and this lycopene pigment is having 11 conjugated double bonds, and due to this 11 conjugated double bond in lycopene, the wavelength of lycopene is 800 nanometer, and due to this 800 nanometer, the 800 nanometer wavelength, nearly 800 nanometer wavelength is a part of visible spectrum. So as 800 is a part of visible spectrum, and the 800 is giving red color to the tomato. So this is very important thing. Whenever any part of the nature is absorbing visible light, then it shows color to us, and such things are colored and they are visible to us. So this is very important about electromagnetic radiations and electromagnetic spectrum. Now I will go in detail about the visible spectrum. So students, you can clearly see here, so different types of wavelengths are given. So 400 nanometer, 450 nanometer, 500 nanometer, 550 nanometer, 600 nanometer, 650 nanometer, 700 nanometer, and 750 nanometer. The different kinds of wavelengths are given, and these wavelengths are a part of visible spectrum. So why I have placed this slide here? Because it is very important to understand which wavelength correspond to which color. Now, you can see the left part of the visible spectrum, and it is very important as far as UV visible spectroscopy is concerned. The left part of the spectrum is blue in color. And if we go to the right part of the spectrum is red in color. So whenever compounds are absorbing light and that are in the red part of the spectrum, such compounds are red to us. And whenever blue part of the spectrum, blue part light is absorbed by the compound, then they appears as a blue. So these colors are very important, and we must understand which color gives which wavelength gives which color. So this is very important for us. Rajput sir. Hello. Hello. Rajput sir. So,
Hello.
sir,
Sir.
as sir,
Hello.
now I would like to share the screen from the laptop.
Yes, sir. Yes, sir. No issue, sir. Proceed,
Okay.
sir.
Okay, I have registered from the different account. So please make that account host for me. Then I will talk from the laptop.
Okay. I will speak to host, sir. Huh? Okay.
Okay, sir.
Adole, sir.
Yes, sir.
You are now co-host. Please share screen of laptop.
Adore sir, you are not audible.
Okay. Right now am I
Yes,
audible?
sir. Yes, sir. Yes,
Okay.
sir.
Okay. Thank you very much for cooperation. Now, dear students, as I discussed with you, this visible spectrum is very important for us as different types of lens are giving different type of colors. So we will go in detail in the next slides. Now, this all part was the basic part as far as spectroscopy is concerned, and I have discussed with you why spectroscopy is important for us. Now, dear students, let us understand different terms which are in spectroscopy. So first of all, I would like to discuss with you what frequency means to us. Now, dear student, you can see here the wave is given, and here the upper part of the wave, positive displacement in the wave means crest. And whenever there is a negative displacement is called as trough. So this is very important for us to understand. The positive displacement in the wave is called as crest, and the negative displacement is called as trough. And the distance between two successive crests. So you can see here in this slide, so I have shown the wavelength. This distance, that is distance between two successive crests, is known as wavelength. You can also take the distance between two successive trough. It is also called as wavelength. So wavelength is nothing but distance between two successive crest or two successive trough. Now, the another important part which we must understand is frequency. Now, what is frequency? So frequency is nothing but number of oscillations, number of cycles per second. Now, let us understand how many oscillations are given in this slide. So dear students, you can see here. So we must understand how many oscillations are given here in this slide. Now one oscillation means one crest and one trough. So you can see here, this is crest and this is trough. So this crest and trough is forming one cycle in the wave. And the second cycle is this one crest and trough. So one crest and one trough is forming one cycle. In this way, you can see here there are total 5 crests and 3 crests and 2 troughs are given. This means that as one crest and one trough is forming one cycle, this means that there is presence of 2.5 cycles per second. I have shown here wave per second. So 2.5 cycles are there per second. This means that the frequency is 2.5 cycle per second. And dear student, 1 cycle per second is called as 1 hertz. And as there is presence of 2.5 cycles per second, this means that 2.5 hertz frequency is there. So it is very important to understand what frequency and wavelengths are there in spectroscopy. So wavelength is nothing but distance between two successive crests or distance between two successive trough, and frequency is nothing but number of cycles per second. So here in this wavelength, I have shown 2.5 cycles per second, and 1 cycle is equal to 1 hertz. So these two terms are very important as far as TY-BSc syllabus is concerned. Now friends, as I discussed with you, whenever light is passed through the sample, whenever light is passing through the matter, light can be absorbed by the matter. Now let us understand what this absorption of light gives to us. Now I have written here the ground state and excited state in the matter. In any molecule, we know that there are presence of various states, and molecules are at room temperature always prefers ground state. So there is presence of ground state and excited state. The difference between these two states I have taken here as a 3 electron volt. Electron volt is also a form of representation of energy. So difference between ground state and excited state is taken as a 3 electron volt to understand the concept of light absorption. Now, as we know that molecules at room temperature always prefers ground state. So let us consider molecules are present at a ground state. And now the difference between ground state and excited state is 3 electron volt. This means that 3 electron volt energy is required to go from ground state to excited state for a molecule. So molecule can go to excited state if it gets 3 electron volt energy from the electromagnetic radiation. So whenever light is passed, so what is going to happen? Whenever we will supply 3 electron volt energy, then molecule will undergo excitation, transition from ground state to excited state. So this is going to happen whenever light is absorbed. So absorption of light gives excitation. Excitation is also called as transition from ground state to excited state. And here, as the difference is 3 electron volt, the 3 electron volt energy is required. Now let us consider, dear students, if we supply 2 electron volt energy, if we supply 2 electron volt energy, what is going to happen there? Now, as excitation requires 3 electron volt energy, the excitation from ground state to excited state requires 3 electron volt energy. By supplying 2 electron volt energy, there will be no excitation from ground state to excited state. Why there is no excitation? Because excitation requires 3 electron volt energy and we are supplying less than that. Excitation is requiring 3 electron volt energy. So if we supply energy less than 3 electron volt, the energy will not be absorbed by the sample
and as energy is not absorbed, energy will pass as it is. So excitation requires that energy which is the difference between two states. So here difference between two states is 3 electron volt. So we must supply energy corresponding to 3 electron volt. If we supply energy less than 3 electron volt, there will be no excitation from ground state to excited state. So here, dear student, we must understand what is happening whenever light is absorbed. So whenever light is absorbed, there will be excitation of molecules from ground state to excited state. Again here, I would like to point out one thing. Whenever light is absorbed, there will be different kind of excitation based on what kind of light is used. We know there are different types of spectroscopic techniques: UV visible, IR spectroscopy, NMR spectroscopy. Now, these spectroscopic technique involve use of different lights, and as different lights are used, we are getting different type of excitations. Whenever you will learn all these spectroscopic technique, you can easily point out the different electronic excitations, a different type of excitation in the sample. Now, here we know that whenever light is absorbed, the molecule is going to excite from ground state to excited state. Now, let us discuss the main part of today's lecture, that is UV visible spectroscopy. Friends, this spectroscopic technique, as I discussed with you, is very important to find out two important things. First thing is conjugation can be predicted. We will see what is exactly this conjugation. And second thing, we can find out stereochemistry of the alkenes. That is, we can differentiate the stereochemistry, we can differentiate the configuration cis and trans. One thing I would like to point out here, UV visible spectroscopy is also called as electronic spectroscopy. I will discuss with you why it is called as electronic spectroscopy. So friend, this technique is very important for all types of chemistry student. This topic is included in TYBSc chemistry syllabus, MSc chemistry syllabus, and if you are preparing for IIT JAM, it is also important for IIT JAM. Then set examination, NET, GATE, PhD entrance examination, and also for other type of chemistry based government examination. So this topic is very important as far as different type of competitive examinations are concerned. So friends, now let us understand the electromagnetic spectrum in UV visible spectroscopy. Friends, in the first two slides, I discussed with you different types of radiations are there. And one of the radiation, that is UV visible radiation, is having a particular wavelength. It is having particular energy. Now, first of all, I would like to point out here, there are two types of UV visible region. And these two UV visible regions are ultraviolet and visible. So as the name itself indicates, there is presence of UV region, ultraviolet region, and visible region. So here we must remember what type of wavelength is present in ultraviolet and visible region. So in ultraviolet region, here I have written a wavelength. So in examination, they may ask you what is the wavelength of ultraviolet region. So ultraviolet region is having 10 nanometer to 400 nanometer wavelength, and visible region starts from 400 to 800 nanometer. So they may ask you the UV visible part of the spectrum is having what type of wavelength. So you can note down here 10 nanometer to 400 nanometer is the ultraviolet part, and 400 to 800 nanometer is the visible part. Then the ultraviolet is further divided into two types, and these two types are near ultraviolet and far ultraviolet. Near ultraviolet starts from 200 to 400 nanometer, and far ultraviolet region is below 200 nanometer. And this far ultraviolet region is not important at all as far as UV visible spectroscopy is concerned. The important part of the electromagnetic spectrum, important part of the UV visible spectrum is from 200 to 400 nanometer and from 400 to 800 nanometer. This far ultraviolet is not important at all. Dear students, again I am repeating, UV visible regions are of two types, ultraviolet type and visible type. Ultraviolet has wavelength range 10 nanometer to 400 nanometer. Visible has wavelength range 400 to 800 nanometer. And ultraviolet is further divided into near ultraviolet and far ultraviolet. Far ultraviolet has wavelength below 200 nanometer. Near ultraviolet has wavelength 200 to 400 nanometer. And this far ultraviolet is not important as far as UV visible spectroscopy is concerned. So important part of the electromagnetic spectrum is 200 to 400, 400 to 800 nanometer in the UV visible spectroscopy. Now, let us understand what is the principle of UV visible spectroscopy. So, to understand any spectroscopic technique, we must know how the spectroscopic technique is operating. We must know the principle of that spectroscopic technique. As I am discussing here UV visible spectroscopy, let us understand the principle of UV visible spectroscopy. So, in the first slide, I discussed with you electromagnetic radiations are interacting with the sample. Electromagnetic radiation, nothing but light. Now, dear student, in the UV visible spectroscopy, the electromagnetic radiations, which are also called as UV visible radiations, and these are having wavelength range of 200 to 800 nanometer. 200 to 400 is UV and 400 to 800 is visible. So here the electromagnetic radiations are having energy of 200 to 800 nanometer. We must remember this thing. So here electromagnetic radiations are UV visible radiations. So these UV visible radiations are passed through the sample. Sample means the organic compound which is under study. So the electromagnetic radiations are passed through the sample. And whenever electromagnetic radiations are passed through the sample, whenever UV visible radiations are passed through the sample, the thing which is going to happen is excitation. As I discussed in the previous slide, whenever molecules, whenever sample absorb the radiation, it goes from excited ground state to excited state. Now here, what happens in the UV visible spectroscopy, whenever UV visible light is absorbed by the sample, the electrons get excited. There is excitation of electron from lower energy level, that is ground state, to the excited state. So there will be excitation of electron, and excitation of electron is called as electronic excitation. So dear student, we must remember what is happening whenever UV visible radiations are passed through the sample. The thing which is happening here is excitation of electrons from lower energy level to higher energy level. So there is electronic excitation in UV visible spectroscopy. And as I discussed in the previous slides, that UV visible spectroscopy is also called as electronic spectroscopy. Now, you must understand why it is called as electronic spectroscopy. Because in UV visible spectroscopy, electrons are excited from lower energy level to higher energy level. There is excitation of electron. Therefore, UV visible spectroscopy is called as electronic spectroscopy. So this is the simple principle of UV visible spectroscopy as far as organic chemistry is concerned. So there is excitation of electrons. Now, as there is electronic excitation, as UV visible light is absorbed by the sample, this amount of light absorbed by the sample is recorded in the instrument. It is recorded in the instrument. And whenever amount of light absorbed by the sample is recorded, we get a plot. We get a plot, and that plot is called as spectrum. Spectrum is giving, the UV visible spectrum is nothing but a plot of absorbance versus wavelength. So the instrument records the amount of light absorbed in the form of a plot, and the plot is called as UV visible spectrum. And UV visible spectrum is a plot of absorbance versus wavelength. So it is a plot of absorbance versus wavelength. And now here, the absorbance is very important. So to this axis, absorbance increases from 0 to onwards, and to this axis, there is wavelength. Now, it becomes very important for a chemistry student to understand the nature of this UV visible plot. Let us understand this UV visible spectrum. So you can see here, there is presence of two hills. We can say there is presence of two upward hills. Two hills are present in the spectrum, and these two peaks, these two hills are called as peaks in the spectrum. Whenever you see the spectrum, these are called as peaks. These are called as signals which are recorded in the spectrum. Now this first part, you can see here, this first part is to the above side. It means that here on this axis absorbance is given. So this peak one indicates it is having higher absorbance value as it is above in the spectrum. And this second one is below in the spectrum, indicates it is having lower absorbance value. So we can easily say in the UV visible spectrum which is having higher absorbance value, which is having lower absorbance value. Higher absorbance value means it is absorbing light repeatedly. Lower absorbance value, it means it is absorbing light with less amount. Now on this axis wavelength is written. Dear students, you can see this second peak is to the right hand side. So as it is to the right hand side, second peak is having higher wavelength and first peak is having lower wavelength. So you can say that absorbance value of first peak is greater. However, the second peak is to the right hand side, so wavelength of the second peak is written. So this type of graphs, this type of plots are obtained whenever UV visible spectrum is recorded. So we must understand the plot is absorbance versus wavelength, and the spectrum, UV visible spectrum, looks like this. So there will be higher absorbance value peak, lower absorbance value peaks. There may be one peak, there may be two peaks, there may be three peaks. So in this case, I have taken example in which two peaks are there, and deliberately I have taken two peaks in a such a way that we can understand which one is having higher absorbance value and which one is having higher wavelength value. So here we can easily read the UV visible spectrum. So in this way, dear students, we are getting the UV visible spectrum, and as I discussed with you, there will be electronic excitation in UV visible spectroscopy. Now let us understand what type of electrons are present in the organic compound. Now dear students, you might be wondering why I have taken this slide, that is types of electron. As I discussed with you, UV visible spectroscopy is involving excitation of electron from lower energy level to higher energy level. We must understand electrons also. As there is electronic excitation, we must understand the types of electrons in organic compounds. So as we are studying in the TY basic chemistry, we must know how many types of electrons are there in the organic compounds. So the types of electrons are of two types. These two types are bonding electrons and non-bonding electrons. And now we must understand what this bonding and non-bonding means. Bonding electrons are the electrons which are a part of bonds. Non-bonding electrons are not a part of bond. Let us understand this concept in detail. Dear students, I have taken example of phenol to understand types of electrons. So we know that in phenol there is presence of sigma bonds and pi bonds. We know what sigma and pi bond means. So here this single bond is a sigma, and whenever there is double bond is having one sigma bond and one pi bond. And as sigma and pi are bonds, this means that sigma bond and pi bonds are having bonding electrons. As sigma and pi are bonds, the electrons present in the bond will be bonding electrons. So sigma electrons and pi electrons are bonding electrons. Now on oxygen, I have shown lone pair of electrons. Lone pair of electrons, also called as unshared electron pairs, and unshared electron pairs are not a part of bond. They are not part of bond, therefore they are called as non-bonding electrons. So dear students, we must remember here, whenever there is presence of heteroatom such as oxygen, nitrogen, chlorine, bromine, sulfur, all these heteroatoms are having lone pair of electrons, which are also called as unshared electron pairs, and these unshared electron pairs are not part of bond, called as non-bonding electrons, and the bonds involved in sigma and pi bonds are called as bonding electrons. So in this way, there is presence of bonding electrons and non-bonding electrons in organic compounds. Now, to understand the UV visible spectroscopy, another important point which is very crucial for the student is LCAO principle. Dear student, let us understand LCAO principle. We will take a break of 1 minute, then I will proceed again. Okay. So students, for understanding any spectroscopic technique, we must understand what is LCAO principle. Friends, dear students, LCAO means linear combination of atomic orbital principle. Now, according to this principle, whenever n atomic orbital combines, they forms n molecular orbitals. And here I have taken a very simple example. Whenever two atomic orbital combines, they will form two molecular orbitals. So LCO principle means the number of atomic orbital which are combining to form molecular orbital will form that number of molecular orbitals in LCO principle. So here I have taken example. Whenever two atomic orbitals combine, they will form two molecular orbitals. And we know how molecules are formed. Molecules are formed by the combination of atoms. So here we must understand atoms are having atomic orbitals and molecules are having molecular orbitals. Another important thing about LCO principle is out of the total molecular orbital which are formed, then in that case, if the number of molecular orbitals are even, so here two number is even. So whenever even molecular orbitals are formed, these even molecular orbitals will form even molecular orbitals will contain 50% bonding molecular orbitals and 50% anti-bonding molecular orbitals. So there is presence of two types of molecular orbital. One is bonding, another is anti-bonding.
Sir, not audible. Adole sir. Hello. Adole sir. Dear student, wait for 2 minutes only. Adole sir. Adole sir.
Okay.
Yes, students, wait.
Am I audible now, sir? Sir, am I
Yes, sir.
audible?
Yes, yes.
Audible, sir.
Okay. Now
Yes, sir.
I am audible, I think.
Yes,
Dear
sir.
students,
Yes, sir, you are
we
audible.
know that in organic compounds, there is presence of sigma electrons, pi electrons, and non-bonding electrons. And at this point, we also know that UV visible spectroscopy involves electronic excitation. So, dear students, there are various types of electronic excitation that are taking place in UV visible spectroscopy. As there is presence of three different types of electrons: sigma electrons, pi electrons, non-bonding electrons. These electrons will give us different type of electronic excitation in UV visible spectroscopy. Now, let us understand different energy levels in this diagram. So you can see here, the two green levels are written here, and these two green levels are representing bonding electrons. So I have deliberately chosen a color, different colors here to represent different type of orbitals. So here, sigma orbital, sigma bonding molecular orbital is written at the bottom. Above to sigma, there is pi bonding orbital. And above to pi bonding orbital, there is non-bonding orbital. And after that, pi star, that is pi antibonding, and sigma star, sigma antibonding. So, dear students, you might be wondering about these energy levels, but I will clear your doubt here by explaining the energy levels. So I would like to tell you here, we know one thing, sigma bonds are stronger bonds than pi bonds. And as sigma bonds are stronger than pi bonds, sigma bonds are more stable than pi bonds. And as sigma bonds are more stable, they are written at the bottom. Sigma bonding molecular orbital is written at the bottom. And pi bonding molecular orbital is written above to the sigma. It means that pi bonding molecular orbital is slightly less stable than sigma bonding molecular orbital, and this is only due to strength of the sigma and pi bond. And then in the energy level diagram, you can see non-bonding molecular orbital is non-bonding orbital, not molecular orbital. Non-bonding energy level is above to the pi bonding. This is because sigma and pi are part of bonding, and non-bonding is not a part of bonding. As it is not part of bonding, it means that it is more unstable as compared to sigma and pi. Its stability is less, and as its stability is less, it will have more energy. This is the energy sequence, energy level diagram. So here comes the more stable sigma, then comes pi, and then comes less stable non-bonding. So in this way, three orbitals are placed. And secondly, the pi and sigma antibonding molecular orbitals, that is pi star and sigma star, these are antibonding. Antibonding means they are not forming the bond, and as they are not forming the bond, they are highly unstable, and as they are highly unstable, they are above in the energy level diagram. So in this way, we know why different types of orbitals are written here according to various type of energy sequence. So sigma, then comes pi, then comes non-bonding, then comes pi star, then comes sigma star. So sigma more stable than pi, pi more stable than n more stable than pi star more stable than sigma star. So in this way, different type of energy levels are given here. Now, as I discussed with you, there is electronic excitation in UV visible spectroscopy. We must understand how electrons are excited, how electrons are promoted from lower energy level to higher energy level by absorbing energy. So you can see here the first upward arrow. In the first upward arrow, the electron is excited from sigma to sigma star. So you can see the upward arrow is mentioning, upward arrow is giving idea about electrons are excited from lower level to higher level. So first upward arrow is for sigma to sigma star electronic excitation. It means that in this condition, electrons are excited from sigma orbital to sigma star orbital. So this is first type of electronic excitation, that is called as sigma to sigma star. Second, you can see here, in the second type, I have given the arrow from n to sigma star. That is, electron is excited from non-bonding orbital to the sigma star orbital. Then the third arrow, you can see electron is excited from pi orbital to pi star orbital. And in the last case, the electron is excited from n orbital to pi star orbital. There is n, mistakenly V is written, as I am playing the PowerPoint in mobile, so there should be n. Okay, so in the fourth case, electron is excited from n to pi star. In this way, electrons are excited from sigma to sigma star, non-bonding to sigma star, pi to pi star, and n to pi star. So you can easily say there is presence of four types of excitation, electronic excitation, in UV visible spectroscopy. Now, dear student, there may be one question in your mind, and that question is, why electrons are excited to star orbitals? Star orbitals means antibonding molecular orbitals. I would like to point out here, generally, the bonding molecular orbitals, that is sigma and pi, these orbitals are having electrons. As they are bonding, they contain electron, and antibonding molecular orbitals are empty. Usually antibonding molecular orbitals are empty. So as they are empty, electrons are transferred to them. Electrons are excited to them. So This is the reason why electrons are excited to anti-bonding molecular orbital. Anti-bonding molecular orbitals are empty. So dear student, you remember there is presence of 4 types of electronic excitation in UV visible spectroscopy, and these excitations are sigma to sigma star, then pi to pi star, n to sigma star, and n to pi star. Now it is very important for the students to understand how much energy is required for different kind of electronic excitation. So dear students, you can see here the distance between sigma orbital and sigma star orbital is large. As distance is large, you can easily predict that this excitation, that is sigma to sigma star excitation, requires more energy for electronic excitation as distance is large. And you can easily see all other distances. Based on these distances, different type of energy is required. If the distance is large, more energy is required. So energy wise, we can say that sigma to sigma star requires more energy. You can see here in this slide, in the yellow part of the slide, I have given sigma to sigma star requires more energy. Then n to sigma star, then comes pi to pi star, and then n to pi star. This energy level gives us idea that n to pi star energy level is having minimum distance. There is minimum distance between n to pi star. You can see in the diagram, n to pi star is having lowest energy difference, and therefore as it is having lowest energy difference, the n to pi star requires less amount of energy for the electronic excitation. Dear students, we know one energy equation, E is equal to h nu. We know this energy equation, E is equal to h nu, and in this equation, nu is the frequency, and nu can be written as C upon lambda. In the energy equation, energy is inversely proportional to wavelength. Again, I am repeating, energy is inversely proportional to wavelength, and as energy is inversely proportional to wavelength, this means that if energy is high, wavelength will be low, and if wavelength is low, energy will be high. If energy is low, wavelength will be high. This is because energy is inversely proportional to wavelength. And as here in this diagram, as I discussed with you, sigma to sigma star requires more energy for electronic excitation. According to the relationship between energy and wavelength, you can easily say that sigma to sigma star shows less wavelength in UV visible spectroscopy, and n to pi star orbital requires less energy for electronic excitation. It means that it will show high wavelength. So wavelength sequence is written at the bottom. It indicates n2 pi star is having more wavelength than pi to pi star. Pi to pi star is having more wavelength than n2 sigma star, and n2 sigma star is having more wavelength than sigma to sigma star. This is totally based according to the energy equation. Energy is inversely proportional to wavelength. So dear student, in the examinations, examiners will ask you what kind of electronic excitations are there in UV visible spectroscopy, and arrange them in the energy sequence and also in the wavelength sequence. So you have to understand there is presence of 4 types of electronic excitation, and here I have arranged them in the energy sequence as well as wavelength sequence. Now dear student, another important point we must learn here, when there will be sigma to sigma star, n to sigma star, pi to pi star, and n to pi star transition, what type of compound show this transition, we must understand in this lecture. So with this I will move forward, and we will see different types of examples indicating different type of electronic excitation. Let us take this first example. Dear students, I have taken example of alkane. So first thing which I would like to tell you, all organic compounds contain sigma bond. Without sigma bond, there is no organic compound. And as all organic compounds are having sigma bond, all organic compounds will show electronic excitation sigma to sigma star as they are having sigma bond. So alkenes, we know alkenes contains only sigma bond. So alkenes will show sigma to sigma star electronic transition. So we can say that alkanes show sigma to sigma star transition. Dear students, let us see the second example, N2 sigma star. Here the S is sigma. Due to PowerPoint presentation in mobile, the symbol is not taken by this PowerPoint. So it is N2 sigma star transition. It is N2 sigma star transition. Now, N means non-bonding electron. And dear students, we know that non-bonding electrons are present in those compounds which contain heteroatom, such as oxygen, nitrogen, fluorine, chlorine, bromine, etc. So friends, whenever heteroatoms are present, and heteroatoms are part of sigma bond, we know sigma bonds must be there in organic compound. So due to this sigma bond and heteroatom, such a compound will show N2 sigma star transition. So alkyl halides, I have taken example of chloroethane, bromoethane, then ethylamine, ethyl alcohol. All these compounds are having sigma bonds along with non-bonding electron. So they will show N2 sigma star transition. So such a compound show N2 sigma star transition. Let us see third example. Dear students, now I would like to discuss with you N2 pi star transition. Now, as the name itself indicates, non-bonding and pi star is there. So whenever pi bond is there and pi bond is having heteroatom, then there will be excitation of electron from non-bonding to pi star. So you can see here in this slide. So I have taken example of phenol, aniline, acetone, and the nitrile compound. So in the phenol, pi bonds are present and also non-bonding electrons are present. In the aniline, pi bonds are present and also non-bonding electron of nitrogen is present. And in also other cases, non-bonding and pi electrons are present. This indicates that all these compounds will have excitation of electron from non-bonding orbital to pi star orbital. Let us take the fourth example. Now, I have taken example of benzene, ethylene, and acetylene. All these compounds are having pi bond, so they will show pi to pi star transition. So in this way, we must understand what type of transitions are present in particular compound. So you can say all organic compounds are having sigma to sigma star transition. In all four cases, there will be sigma to sigma star transition. Additionally, whenever there is non-bonding electron, there will be N2 sigma star. Whenever non-bonding with pi orbital, there will be N2 pi star. Whenever there will be only pi bonds, there will be pi to pi star electronic excitation. Again, I'm pointing, all these compounds will have sigma to sigma star. So along with sigma to sigma star, they can have N2 sigma star, they can have N2 pi star, they can have pi to pi star. So in this way, we learned about what kind of electronic excitations are there in the organic compounds. Now, another important thing, which is very important as far as UV visible spectroscopy is concerned, is different type of terms which are there in the UV visible spectroscopy. The first term, which is very important for us, is chromophore. Dear students, let us understand what is chromophore. Chromophore is any type of organic group. Chromophore is any type of organic group which can absorb UV visible radiation. Means if it absorbs the UV visible radiation, then such a type of groups can be called as chromophores. So any type of group which are capable of absorbing UV radiation are called as chromophore. And due to these chromophores, there are different type of colors to the objects, to the compounds. Now, I would like to point out here, I have taken example of NO2, NO, C double bond O, C double bond N, C triple bond N, C double bond C, and C double bond S. All these types of groups are having double bonds. And whenever double bonds are present, double bonds are having absorption in the 200 to 800 nanometer. So these types of double bonds can absorb the UV radiation, and all these groups can be called as chromophore. So dear students, the groups which absorb UV visible radiation are called as chromophore. And how to identify chromophore? In the chromophore, there will be presence of multiple bond, that is double bond and triple bond. So in this way, we can identify chromophores in the organic compound. Second term, which is very important for us, is oxochrome. Dear students, oxochrome are the groups which does not absorb the UV radiation. UV radiations are not absorbed by the oxochrome. But how to define the oxochrome? Whenever oxochrome is attached to chromophore, whenever oxochrome is attached to chromophoric group, then they increases the wavelength. They increases the wavelength of chromophore. Again, I am repeating, oxochrome itself does not absorb the UV radiation, but when oxochrome is attached to chromophore, it increases the wavelength of chromophore. I will take the example. Here, in the bottom part of the slide, you can see benzene is there. And dear friends, dear students, as benzene is having multiple bonds, you can say that benzene is having chromophore. Chromophore means multiple bonds. So benzene is having chromophore. So benzene will absorb UV radiation, because definition of chromophore is groups which are able to absorb the UV radiation. So benzene is a chromophore. And I have shown the wavelength of benzene. Benzene absorbs 255 nanometer wavelength. So benzene is absorbing UV radiation. Second example, I have taken phenol. Dear student, this is the structure of phenol. And in phenol, you can easily see the lambda max is given. Lambda max means highest wavelength which is absorbed by the compound. So phenol is showing 270 nanometer wavelength. It means that going from benzene to phenol, there is increase in wavelength. Wavelength is increased. And why wavelength is increased? Dear students, in the phenol, OH group is present. And OH group, when attached to the benzene, is increasing wavelength. Here I would like to point out, this OH group is having sigma bond. We know oxygen hydrogen bond is sigma bond. So OH is having sigma bond, and sigma bond, whenever sigma bond is present, it is called as oxochrome. And whenever double bond is present, it is called as chromophore. So OH is a oxochrome, and OH is attached to benzene. And you can easily see the wavelength is increased. So oxochrome is the group which increases the wavelength of chromophore. So wavelength of benzene is increased to 270 nanometer due to attachment of OH with the benzene. Let us take the third example, aniline. So friends, again there is benzene in the aniline. Now benzene is called as chromophore as it is having multiple bonds. I have defined what is meant by chromophore. Now NH2 is attached to benzene and NH2 is having sigma bonds. Two hydrogens are sigma bonded to nitrogen. So NH2 is called as oxochrome. And due to attachment of oxochrome, that is NH2, with the benzene, the wavelength is increased. So in this way, we can say that oxochromes are the group whenever attached to the chromophore increases the wavelength. So there is increase in wavelength whenever oxochrome is attached to chromophore. This is very important point regarding oxochrome. So again, I am repeating, dear students, chromophore absorb UV radiations and these are multiple bonded groups. Oxochrome does not absorb UV radiation as they are having sigma bonds, and these are generally sigma bonded groups. So here I have taken example of CH3, OH, OCH3, NH2. All these are oxochrome. Let us move forward and let us understand another term which is used in UV visible spectroscopy, and it is bathochromic shift. Dear student, let us understand bathochromic shift. Whenever the wavelength of any compound increases, it is called as bathochromic shift. So increase in wavelength is called as bathochromic shift, and this bathochromic shift is also called as red shift. In the first few slides, I discussed with you visible spectrum. In the visible spectrum, red part is to the right hand side, left part is to the blue part is to the left hand side. In the visible spectrum, red part is to the right hand side and blue part is to the left hand side. And red part is having higher wavelength and blue part is having lower wavelength. Already I have discussed with you. And as I discussed here with you, bathochromic shift is shift in wavelength which is to the higher wavelength. So whenever wavelength increases, it is called as bathochromic shift. And bathochromic shift is also called as red shift, because red part of the visible spectrum is having higher wavelength. Here, I have taken example of paranitrophenol. Dear students, you can see paranitrophenol. In paranitrophenol, resonance is taking place from OH to benzene, benzene to nitro group. And this problem is very important as far as university exams are concerned. Paranitrophenol is treated with base. Every student knows the function of base. Base abstracts the proton. And whenever proton is abstract, negative charge is formed. So base is abstracting proton from OH and it forms a negative ion. It is called as paranitrophenol. Dear student, you can see in paranitrophenol, oxygen is having 2 lone pairs. And in the right hand side, paranitrophenol, oxygen is having 2 lone pair with 1 negative charge. Means it is having 3 lone pairs in the paranitrophenol. So you can easily tell which is more electron rich, which oxygen is more electron rich. So the oxygen, phenoxide oxygen, is more electron rich than the phenol oxygen because it is having more electrons. And as it is having more electrons, you can say that there will be easy excitation of electron. As it is having more electrons, there is more resonance in the paranitrophenol due to presence of more electrons. So the phenoxide is having more electrons. It requires less energy for electronic excitation. And we know the relation between energy and wavelength. As it is requiring less energy, it will have more wavelength. So you can see paranitrophenol is having lower wavelength and the paranitrophenol is having higher wavelength in this reaction. So going from paranitrophenol to paranitrophenol, wavelength increases. So we can say that in alkaline medium, paranitrophenol shows red shift because negatively charged oxygen delocalizes more effectively than unshared electron pair in phenol. So there is increase in wavelength. So paranitrophenol shows bathochromic shift, which is also called as red shift. Let us understand another term, hypsochromic shift. Dear students, hypsochromic shift is the shift where wavelength decreases. And as wavelength decreases, it is also called as blue shift. Blue part of the visible spectrum is having lower wavelength. So when wavelength is less, it is called as blue shift and it is hypsochromic shift. So decrease in wavelength is hypsochromic shift, increase in wavelength is bathochromic shift. I have taken one example here. Aniline shows blue shift in acidic medium. Let us understand why aniline shows blue shift. Dear students, you can see here in acidic medium, nitrogen of aniline is protonated and it forms anilinium ion. So left hand side aniline is present, right hand side anilinium ion is present. And we know whenever nitrogen donates electron to the proton, then the protons are not there on nitrogen. So in anilinium ion, protons, electron pair of nitrogen is donated to proton. It means that there is no nitrogen, there is no electron pair on nitrogen in anilinium ion. Anilinium ion is to the right hand side. Whereas in aniline, electron pair is present on nitrogen. As electron pair is present on nitrogen, there will be resonance in the aniline from nitrogen to benzene. And in anilinium ion, as there is no presence of electron on nitrogen, electrons are absent on nitrogen, there will be no resonance from nitrogen to benzene. Another thing, as I discussed with you, various types of electronic excitations, you can easily predict the aniline is having non-bonding electron and also pi bond. So it is having N2 pi star electronic excitation. Along with N2 pi star, the aniline is also having pi 2 pi star excitation as pi bonds are present. So I am repeating, aniline is having pi 2 pi star excitation due to double bond, and it also has N2 pi star electronic excitation due to lone pair and pi bond. Now, going from aniline to anilinium ion, you can see double bonds are present. So aniline will show pi 2 pi star transition. However, lone pair of electrons are absent on nitrogen. it indicates that N2 pi star transition is not present in anilium ion as there is no non-bonding electron on nitrogen. One thing which I discussed with you, that N2 pi star electronic excitation requires lowest amount of energy. And as it requires lowest amount of energy, it will show higher wavelength. So aniline has N2 pi star transition, but anilium ion does not have N2 pi star transition. So due to presence of N2 pi star transition, aniline has a higher wavelength and anilium ion has lower wavelength. So going from aniline to anilium ion, wavelength decreases, and decrease in wavelength is called as hypsochromic shift, and hypsochromic shift is also called a blue shift. So dear student, you can easily say that aniline shows blue shift, that is hypsochromic shift in acidic medium. So in this way, we have understood about the bathochromic shift and hypsochromic shift. Dear student, let us understand another term which is used in UV visible spectroscopy, and it is hyperchromic shift. Hyper means increase, and hyperchromic shift is called when there is increasing intensity of color. So going from faint red to bright red, there will be increase in intensity of color. And when intensity of color increases, it is called as hyperchromic shift. Going from faint yellow to bright yellow, there will be increase in intensity of color. It is called as hyperchromic shift. I have taken example of pyridine and 2-methylpyridine. Dear student, you can easily see the another important thing I would like to tell you. The intensity is represented, color intensity is represented by epsilon, molar absorptivity. In physical chemistry, you have learned this thing, molar absorptivity. So molar absorptivity indicate intensity of color. In the pyridine, you can see it is having epsilon, that is molar absorptivity 2750, 2750. And in the 2-methylpyridine, you can easily see the molar absorptivity is 3550. So going from pyridine to 2-methylpyridine, the molar absorptivity is increased. Molar absorptivity increase means intensity is increased, and as color intensity increases, it is called as hyperchromic shift. So 2-methylpyridine shows hyperchromic shift when compared with pyridine. Another important term which is very crucial in UV visible spectroscopy is hypochromic shift. Now hypo indicate lower, decrease. So hypochromic shift means when intensity decreases, it is called as hyperchromic shift. So decrease in intensity is called as hypochromic shift. Increase in color intensity is called as hyperchromic shift. Now let us understand all these four terms in one diagram: bathochromic shift, hypsochromic shift, hyperchromic shift, hypochromic shift. So bathochromic and hypsochromic are related to wavelength. Hyperchromic and hypochromic are related to color intensity. So here in this diagram, see carefully, whenever it is to the left hand side, I have indicated by blue arrow. Whenever it is to the left hand side, wavelength decreases, it is called as blue shift, hypsochromic shift. Whenever wavelength increases, it is moving to the red part of the visible spectrum, it is called as red shift, bathochromic shift. And whenever absorbance value decreases, it is moving downward. Peak intensity will decrease, color intensity will decrease. It is called as hypochromic shift. And when color intensity, absorbance value increases, it is moving upward. It is called as hyperchromic shift. So by looking at these terminologies, you can easily predict the different types of intensity, different types of wavelengths in the UV visible spectrum. So dear student, again I'm repeating, bathochromic means red shift, increase in wavelength. Hypsochromic means blue shift, decrease in wavelength. Hyperchromic means increasing absorbance value, increase in color intensity. Hypochromic, decrease in intensity. So in this way, we have understood different types of terminologies which are often used in UV visible spectroscopy. So now we are moving to the last part of today's lecture, and that is the effect of conjugation on absorption wavelength. This is very important point. So first example I have taken ethene. In first example, I have taken a molecule ethene. Second is butadiene. Third is hexatriene. Now, ethylene is having one pi bond. It means that there will be presence of pi and pi star orbital. One pi bond is formed by two atomic orbitals of carbon. Two atomic orbitals of carbon will generate two molecular orbitals, and these two molecular orbitals are pi and pi star. Butadiene is having two pi bonds. One pi bond is formed by two orbitals. So two pi bonds will be formed by four atomic orbitals. Four atomic orbitals will generate four molecular orbitals. So there is presence of pi 1, pi 2, pi 3, and pi 4. You can also call it as pi 1, pi 2, pi 1 star, pi 2 star. Out of 4, 2 are bonding, 2 are antibonding. In hexatriene, 3 double bonds are present. One double bond is formed by 2 atomic orbitals. So 3 double bonds will be formed by 6 atomic orbitals. 6 atomic orbitals will produce 6 molecular orbitals according to LCAO principle. So 6 molecular orbitals, out of 6 molecular orbitals, 3 are bonding, 3 are antibonding. And here I have written pi 1, pi 2, pi 3 as a bonding, pi 1 star, pi 2 star, pi 3 star as antibonding. Now here one new term is introduced, and that term is frontier molecular orbital. Frontier means in front of each other. And here I would like to explain to you HOMO orbital and LUMO orbital. Dear students, HOMO means highest occupied molecular orbital. LUMO means lowest unoccupied molecular orbital. Again, I'm repeating. HOMO means highest occupied molecular orbital. LUMO means lowest unoccupied molecular orbital. Now here, we know in ethylene, one pi bond contains 2 electrons. And these 2 electrons are filled in pi. You can see here in this slide, these 2 electrons are filled in pi molecular orbital. And pi star is empty, antibonding is empty. In butadiene, you can easily see 2 double bonds are present. 2 double bonds means 4 pi electrons. 2 electrons are filled in pi 1. 2 electrons are filled in pi 2. So 4 electrons are filled in pi 1 and pi 2. Pi 3 star and pi 4 star, pi 1 star and pi 2 star are empty. In hexatriene, 3 double bonds are present. 3 double bonds means 6 pi electrons. These 6 electrons are filled in pi 1, pi 2, and pi 3. And pi 1 star, pi 2 star, pi 3 star are empty orbitals. So antibonding are empty in all cases. Now, let us see which is called as HOMO and which is called as LUMO. I will take example of butadiene to understand this concept. Dear student, you can see pi 1 and pi 2 orbital in butadiene. Pi 1 and pi 2 orbital in butadiene contains electron. Means they are filled by electrons. They are occupied by electrons. Whereas pi 1 star and pi 2 star are empty. So they are unoccupied orbitals. Now, as there is presence of 2 occupied orbitals in butadiene, pi 1 and pi 2 star, out of these 2 occupied, pi 1 and pi 2, out of these 2 occupied, pi 2 is above. Pi 2 is highest in the diagram. So pi 2 is called as highest occupied molecular orbital. So in this way, pi 2 is HOMO in butadiene. If we take the example of pi 1 star and pi 2 star, both are unoccupied. And as they are unoccupied, out of 2 unoccupied, one will be LUMO. LUMO means lowest. Which is lowest? In the diagram, pi 1 star. So unoccupied molecular orbital, which is lowest in the diagram, is pi 1 star. It is called as LUMO. And they are in front of each other. HOMO and LUMO are in front of each other. They are called as frontier molecular orbital, FMO. In the third diagram, hexatriene, you can see pi 3 is highest occupied, so it is HOMO, and pi 1 star is lowest unoccupied, it is called as LUMO. So let us see the electronic excitation. In ethene, electrons are excited from pi to pi star. There is energy gap delta E between HOMO and LUMO. In the butadiene, electrons can be excited from pi 2 to pi 1 star. The energy gap is given between pi 2 and pi 1 star. In the hexatriene, electrons are excited from pi 3 to pi 1 star, and the energy gap is given. So you can see from left side to right side, from ethene to butadiene, butadiene to hexatriene, the energy gap between highest occupied molecular orbital and lowest unoccupied molecular orbital is decreased. You can see the distance, delta E in ethene, delta E in butadiene, delta E in hexatriene, the distance is decreased. As distance is decreased, electrons, we know electronic excitation, we know the relationship between energy and wavelength. As energy decreases, wavelength increases. So here in hexatriene, less amount of energy required. Less amount of energy means it will have longer wavelength. So we can say that in the first compound, one double bond is present. In the second compound, two double bonds are there and they are conjugated. In third compound, three double bonds are present and they are conjugated. So increase in double bond decreases the distance between HOMO and LUMO, and this decrease in distance increases the wavelength, and increase in wavelength is called as bathochromic shift. So in this way, we can predict effect of conjugation, effect of increase in double bond is increase in wavelength in UV visible spectroscopy. That is, conjugation increases the wavelength. So, dear friends, now with application of UV visible spectroscopy in organic compound, I will finish my today's talk. So, let us see what are the applications of UV visible spectroscopy. As I discussed in the first slide, UV visible spectroscopy can be used to find out conjugation. In the previous slide, I discussed with you increase in double bond, increase in conjugation, increases wavelength. So if two compounds are there, one is having more wavelength, another is having less wavelength, you can easily say that the compound which is having more wavelength will have more conjugated double bond than compounds having less wavelength. In this way, we can predict the conjugation, type of conjugation, where more conjugation is present. Another thing I would like to tell you, cis and trans compound. These compounds have lower wavelength, trans compounds have higher wavelengths. So if two compounds are given to you, and if you record the UV visible spectrum, and one compound shows higher wavelength, another compound shows lower wavelength, and teacher asks you which is cis compound and which is trans compound, you will tell to teacher that trans compound is having more wavelength, so the compound with higher wavelength is a trans, the compound with lower wavelength is cis. So we can differentiate cis and trans by using the UV visible spectroscopy. Another thing, we can find out certain type of functional group by using UV visible spectroscopy. As I discussed you in earlier slides, phenol shows red shift when it is treated with base, and aniline shows blue shift when it is treated with acid. So by employing this technique, so if you get increase in wavelength by adding base, you can say that there is presence of phenolic functional group, and if you get decrease in wavelength by adding acid, you can say that there is presence of aromatic NH2 group. NH2 group is attached to benzene. So certain type of functional group can be predicted by UV visible spectroscopy. These are three important applications of UV visible spectroscopy. So here I have taken example of cis stilbene and trans stilbene. You can see here, dear student, trans stilbene is having trans geometry, cis stilbene is having cis geometry. And as I discussed with you, trans is having more wavelength. So you can see here, trans is having 295 nanometer wavelength and cis is having 280 nanometer wavelength. So in this way, we can differentiate by using UV visible spectroscopy between cis and trans compounds. So cis and trans can be predicted by UV visible spectroscopy. So with this, I will finish my lecture. For my lecture, I have used three important reference books to prepare this PowerPoint presentation. And these are Introduction to Spectroscopy by Donald Pavia, Elementary Organic Spectroscopy by Y.R. Sharma, and Organic Spectroscopy by Jagmohan. Thank you. Thank you very much.
Hello. 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 Vishnu sir.
Yes, Rajput sir.
Hello, Vishnu sir. Hello, Vishnu sir.
Hello.
Sir, there are some questions
Hello.
from the students. Hi, sir. Adole, sir. There are
Hello,
some questions from students.
sir. Lecture is over.
Hi, sir. Some questions for students, sir.
Hello,
Hi, sir. There are some questions from students.
hello,
Hello. Hi, sir. There are some questions from students.
hello.
Hello.
Hello,
Vishnu, sir. Sir, there are some questions from students. Hello.
hello. Anyone is there?
Hi, sir. Sir, there are some questions from students.
Hello,
Hello.
Rajput
Rajput sir,
sir.
please stop.
Okay.
Vishnu sir,
Hello.
Vishnu sir, can you hear me?
Anyone is there?
Sir,
Sir, my talk is
getting
over.
you're getting our voice, sir. Adole sir.
Hello.
Sir.
Hi, sir. There are some questions from students.
Okay, okay, sir.
Hello.
Hello, am I audible, sir?
Hi, sir. There are some questions from students.
Okay, okay, sir.
Huh.
Let me know
Sir,
the questions.
first question is from Asta Bhanushali. Is it EV visible spectroscopy is useful as quantitative tool?
UV-visible spectroscopy is a qualitative tool, and by using UV-visible spectroscopy, we can find out the type, nature of the compound, and if we consider about quantitative analysis, we can also find out the concentration. How we can find out the concentration? If we took the two example, one is having lower concentration, another is having higher concentration. In the one of the slide, I discussed with you, higher concentration has higher absorbance value, and lower concentrations have lower absorbance value. So by using absorbance value, we can also apply to quantitative determination. So concentration can be predicted, which one is having lower concentration and which one is having higher concentration can be predicted by UV visible spectroscopy.
Okay. Okay, sir. Next question from one of the student Akash Patil. Which type of electrons are involved in EV spectroscopy?
Electrons are actually not evolved in the UV spectroscopy. The electrons are excited within the molecule. So whenever there is presence of, as I discussed with you, sigma, pi, and non-bonding electrons are there. Electrons are excited within the molecule. They are not ejected outside the molecule.
Okay. Sir, next question from Ashutosh Patel. What is difference between hypochromic and hyperchromic effect?
Okay, as I discussed you in one of my slide, hyper means increase, hypo means decrease. So whenever intensity of the color, that is absorbance value of the compound increases, it is called as hyperchromic, and when it decreases, hyperchromic. As first question was there, can we use the UV spectroscopy for quantitative determination? I give the example of lower concentration and higher concentration. Higher concentration has higher absorbance value, so means it is showing hyperchromic shift, and lower concentration having lower absorbance value, so it will show hypochromic shift. There is decrease in absorbance, decrease in intensity in hypo, and increase in intensity, increase in absorbance in hyperchromic shift.
Okay, sir. Last question from Akash Patel. What is mean by chromophore? Example only.
Chromophore. So chromophore is the group which absorb the UV radiation. So whenever compound is having chromophore, then and then the compound can absorb UV radiation. Chromophore means multiple bonded group. So double bond and triple bond can be called as a chromophore. And if you take the example of benzene, benzene has double bond. So benzene can be called as chromophore as it is having double bond. Double bond absorbs UV radiations.
Okay, sir. Thank you, sir. Thank you for the answers of questions which are the questions are asked by our students. Now it's time to vote of thanks. So it's my immense pleasure to give a vote of thanks for today's session. I would like to thanks uh, our chief guest, Professor Vishnu Adole sir, which gives a very dynamic and enthusiastic lecture and very informative and explanatory lecture on UV spectroscopy. It is a part of the TYBSc syllabus of Bombay University. I would also like to thanks to our principal sir, Dr. H.M. Pendekar sir, for encourage us to take such kind of the activities. I would like to thanks Dr. Chetna Patil madam, HOD of Chemistry Department, Arts, Commerce and Science College, Onde, to give a permission to take a such kind of activity or lecture. I would like to thanks to our staff members, Department of Chemistry, Arts, Commerce, Science College, Onde, for the cooperation. Then I would like to thanks Professor Namdev Mahale sir for a wonderful technical support. And last but not least, I would like to thanks to our students, the participants of the today's lecture, and for grand success. I would like to one and all. Okay, thank you, sir, Vishnu sir. Thank you, Male sir, and all the
Okay,
participants.
thank you, sir.
Okay, okay,
Thank you.
okay, sir. Okay, okay.
Thank you, Mahale sir. Thank you, Rajput sir, and thank you, everyone.
Thank you,
Thank
madam.
you all.
Thank you, madam.
Thank you all.
Thank you all. Okay. Thank you.